All right. So this is for the group assignment that we have been asked to do from our data mining module. My name is Ashram Mustafa. My student ID is 0381246. Um, and I will be introducing what we're going to be doing as well as showing my section of the code, which was the clustering section. But yeah, here we go. So in order to get us started, let's talk about what we need, what this is about. So the number of drug deaths in the world, it continues to be a serious problem for public health, especially with the growing number of people who keep abusing opioids and other drugs that are controlled. And because of that, we want to improve prevention strategies for these situations. And we also want to reinforce policies. So it's very important to know the patterns of drug related deaths that happen in the world and the factors that cause them or contribute to them, and the trends that surround them as well. So in this project, we'll be using the data set that we were assigned in assignment 1 to help analyze the number of accidental drug related deaths. And the dataset will include very detailed information such as age, race, sex of the individual, where they died, what drugs they tested positive for, and how they died. And we'll be able to use different data mining techniques to identify patterns, finding groups or individuals who are at risk of accidental drug related deaths, and to develop a bit of insight based on the data that we find. All right, so for that, we use three different types of techniques, and it is clustering. No, we use four actually. It's my bad. We use clustering, we use regression, anomaly detection, and predictive data and classification. Yeah, classification. Sorry, my bad. All right, so I'm gonna go on to my part now, which is clustering.
Hi, my name is Ayham and I'll be going to the classification part of our group assignment for data mining. So the goal for the classification here is to predict whether a case involves opioids using the any opioids column. But first we need to pre-process the data before we can use it. So starting here, this is where we load the dataset using pandas. Right after that, I print the target values just to see the distribution. As you can see here, there are a lot more ones than zeros, which means the dataset is imbalanced. Then in this part I remove unnecessary columns like date, location and descriptions because they don't really help with the prediction. And after that I handle the missing values using the fill and name method. I use this just in case, but since we cleaned the data set for assignment 1, it will have no missing values. And then here I converted the categorical variables into numerical values, and finally I selected only the important features like age, year and the key drugs to reduce the noise and improve its performance. Here I split the dataset into training and testing sets. This is where we do the training, model training. Now that the pre-processing has finished, we will go into model training. So here I split the dataset into training and testing sets using a 0.2, which means an 80 to 20 split, and also I put the random state is set to 42 so the results stay consistent. The 80 to 20 split means most of the data, 80% of the data will be used to train the model and the rest will be used to test it. Then I trained the two models. Uh, we chose decision tree and logistical regression. The decision tree has a max depth of 5 to prevent overfitting, and logistic regression is set with more iterations so it can fully converge. Down here are the results. So the decision tree performs really well. It has around 0.947, which is 94.7% accuracy, and a high F1 score, which means it's very balanced. Logistic regression, on the other hand, has lower accuracy of around 81%, but it has decent recall, meaning it still identifies most opioid cases. Overall, the decision tree clearly performs better across most of these metrics. Here's the confusion metrics for the decision tree. So these values show how the model is predicting, and we can see a high number of correct predictions both for opioid and non-opioid cases. There are very few false positives, but there are some false negatives, meaning a few opioid cases are missed. But overall, the model is performing quite well. Um, and finally, this graph shows the feature importance. You can see that year is by far the most important feature, which suggests there's a strong trend over time. After that, drugs like fentanyl, oxycodone, and methadone also play a role in the data, but the other features have very little impact, as you can see here. So overall classification was successful in identifying opioid-related cases, and the decision tree model performed the best while also giving useful insights into which features matter most.
Okay, so for the clustering steps, first what we did was we loaded the dataset, and as you can see here, we imported a bunch of things: pandas, numpy, matplotlib, seaborn, and then obviously the sklearn stuff, the toolkits that we need for all the clustering methods. So before that, we did a bunch of pre-processing steps in order to ensure the data compatibility as well as the quality of the algorithms themselves. So first we prepared by reading the CSV file, and then we select the specific features as well as the age. So here we are choosing the columns that we believe are necessary, which is heroin, cocaine, fentanyl, oxycodone, ethanol, and benzodiazepine. And for age, we decided to filter the column that exists here, right? And the way we did this was we knew there were missing values here. So we converted the age variable into a numeric format, and then we removed any invalid entries, which ensures that all the data used in clustering, it's valid and very comparable. Beyond that, as you can see here, this is the part where we converted all. As you along here, this is where feature scaling started, and here we use standard scaler. And this step, what it does is it standardizes all the variables to a common scale, and it ensures that no single feature will disproportionately influence the clustering results. And that's very important for distance-based algorithms like k-means, as you can see here. Now, before we go to k-means itself, we did the elbow method. And with the elbow method, uh, we determined the optimal number of clusters. So we calculated the within cluster sum of squares, which is known as WCSS, and it's ranged from it was ranging from 2 to 10. And as for the elbow plot itself, there was a noticeable bend which occurs around k is equal to 4, where the rate of in WCS, sorry, the rate of decrease in WCSS, it begins to slow down. And that really indicates the increasing number of clusters beyond that point, and it like the number of clusters beyond that point provides diminishing returns in improving cluster compactness. So k is equal to 4 was selected as the optimal number of clusters, and that choice, at least for my interpretation, it balances model complexity as well as clustering performance, which means we get meaningful groupings without any overfitting. So here's the code for that part. Now, the k-means algorithm, for that, we again used k is equal to 4 clusters with the k-means the k-means plus plus initialization method to improve centroid selection and convergence. Now, each data point was assigned to the nearest cluster centroid based on Euclidean distance, and these results were then appended to the dataset as a new feature, which allowed us to further analyze and interpret results. There were multiple initializations that were used, as you can see from the n underscore init is equal to 10, as you can see here. And it was done to ensure stability within the program and also algorithm, and it also avoids suboptimal clustering outcomes. So yeah, and when it comes to visualization, we obviously showed the elbow method figures through a scatter plot. Oh, sorry, this is for PCA, my bad. But yeah, for PCA was used, we used a scatter plot, as you can see here. And these were the results that we got from the scatter plot for PCA reduced cluster visualization. As for the elbow method, we have this line graph. Now, when it comes to the when it comes to the results, and with the results, we used 3 different metrics. That were the 3 that you see here, which is silhouette score, the Davies-Bouldin index, and the Kalinsky-Harabash index. And with the silhouette score, the score we got was a 0.23. And this really indicates a model level of cluster separation, which means that while the clusters can be distinguished, there is still a certain degree of overlap to the clusters themselves. As for the Davies-Bouldin index, we got a value of 1.6174. And this kind of shows that there's a level of similarity between clusters, which is a moderate level of similarity. And generally, with the Davies-Bouldin index, we want a lower score, which is why I put here lower is better. And because of how high it is, this kind of indicates that the clusters are somewhat distinct, but they're not perfectly separated. Now, the Kalinsky-Harabash index, we got a really high value, which is good because higher is better. So with that, it really indicates good cluster separation as well as compactness, as higher values usually correspond to better defined clusters. So overall, with all of these results, we are getting an idea that the clustering model is pretty effective with meaningful groupings, despite having a few overlaps here and there. And the use of multiple evaluation metrics generally provides an effective and reliable validation of the clustering performance. We, of course, used PCA, as mentioned before, which is known as principal component analysis, and this was applied to reduce the dataset to 2 dimensions for visualization purposes, of course. And the resulting scattering plot, it shows 4 different clusters, like 4 different types of clusters, color-coded accordingly, with very visible grouping patterns. While there's some overlap, I still think this is readable, and it's also very comprehensive. So from this, we really indicates two things to a lot of us, and that is that certain clusters here, they're clearly separated along they're along their principal components. But another thing is that some clusters, as you can see here, they partially overlap. So it really supports the silhouette score that was mentioned here. And this really confirms that while the clustering structure is meaningful, the boundaries between the clusters are not that distinct. So PCA, it aids in visualizing high dimensional data, and it supports the interpretation of clustering results. So you can see that result here. There is overlap, but at the end of the day, this still works and it's still meaningful results. And there was also cluster profiling done. We calculated the average values of each feature within each cluster, and this also reveals some patterns. So let's look at cluster 0 over here, and there's pretty high heroin presence, and also moderate levels of fentanyl and cocaine. So because of this, the average age is around 46, as you can see here. And this cluster generally represents this cluster generally represents more opioid related cases just because oxycodone is pretty high. Now, cluster 1, we have a high level of cocaine. And because of that, and with the average age being 43.29 years, this pretty much indicates a very high cocaine fentanyl combination case, because fentanyl is the second highest value here. Now, for cluster 2, we have only heroin, and because of that, the average age also being 40, it indicates that we are just representing very heroin dominant cases here, with some moderate polysubstance use with fentanyl and whatnot. And lastly, with cluster 3, we have pretty high ethanol alcohol usage, but we also have pretty high fentanyl usage. So, due to this, with somewhat low heroin and cocaine usage, and the average age for this one is 44.4 years. So, because of that, we have some alcohol related cases where people drink alcohol and mix them with other drugs. So that might reflect a bit of a partying culture that comes with it. And they do have, I mean, these show the different subgroups when it comes to drug related cases, and they identify meaningful subgroups within the data sets, which distinguish between, heroin based prescription, like opioids, cocaine related cases, and fentanyl driven cases. And so, because of that, I'd like to conclude by saying that, this clustering analysis, with all the pre-processing that we did and the cluster selection with the elbow method and implementation of the k-means algorithm and all the scores that we got, I believe we successfully uncovered, distinct patterns in drug-related cases, which highlight different substance usage profiles and demographic trends. And these insights provide a lot of information, a lot of valuable information for further predictive modeling, and it can contribute to data-driven decision making, in the public health space. So yeah.
Hello, my name is Faris and I'm going to be presenting anomaly detection and regression from the applied data mining techniques. First of all, anomaly detection was used to identify the unusual overdose cases that deviated from the normal patterns. Since the dataset we use do not contain any labeled anomalies, we have to use an unsupervised method by which works by randomly partitioning the data and isolating the observations. This is an isolation forest algorithm. Rare and unusual cases are isolated more quickly and making them easy to detect. Before applying this model, we have to first pre-process the data by selecting the relevant features such as the drug indicators and the age group and the sex. which you can see here. And then we had to categorize these variables and encode them into a numerical form, where the data was scaled to ensure consistency across the features. Here you can see that data has been encoded, scaled, and trained by the isolation forest. Next, the isolation forest is trained at the contamination level of 0.03, which is 3% of the whole dataset we expect to be anomalies. The results we got showed that there are 360 anomalies, which is far less than we expected, which is expected since anomalies are rare in the real world situations. Then we generated a bar chart. While only a small number are considered as anomalies, the imbalance between the normal and the anomaly confirms for us that that unusual overdose cases are relatively very uncommon. We also created a scatter plot which further tried to illustrate how anomalies differ from the normal cases. Most observations follow a general pattern, while the anomalies deviate from these patterns. This represents an unusual drug combination or unexpected demographic characteristic. Overall, the anomaly detection helps identify rare and potentially high-risk cases, which can be used for early detection of the emerging drug trends. Next, we have regression. Regression was used to predict the overdose severity. To do this, we needed to create a target variable which represents the total number of the drugs involved in each case. This allows us to model the overdose severity as a continuous variable. Here you can see that we have created a drug count variable and then we preprocessed it by splitting it and encoding. The data set was preprocessed and encoded. By encoding these categorical variables and selecting the relevant features, we then split them into training and testing sets to evaluate the performance. Here you can see that we have split them so that it can be evaluated. The metrics we used for evaluation was the mean absolute error and the RMSE and the R-square. We used linear regression method because it's simple and interpretable and it's effective for understanding the relationship between the variables. And the results actually showed very low error values where R squared value is equal to 1, as you can see here, indicating that the model's predictions closely match the actual values. We also created two diagrams. In a scatter plot, we generated actual and predicted values, and it shows a strong linear relationship confirming a high predictive accuracy. In the residual plot, it shows that the errors are distributed around 0, which indicates the model does not have a significant bias. However, performance this perfect may indicate overfitting or data leakage, meaning that the model may have not been generalized to the new data. Therefore, further validation was needed. Thus, a coefficient analysis was generated so that it can show variables such as cocaine, fentanyl, and heroin, which has the strongest influence. Here is the steps we used to generate the coefficient table. And in the coefficient table, it shows that the drug features have a higher influence compared to the demographic features, where like cocaine, fentanyl, heroin methadone, and oxycodone all have a higher influence than a demographic feature like the race or an age group. This suggests that overdose severity is primarily driven by drug combinations rather than the demographic factors. To conclude, the project successfully applied multiple data mining techniques, including classification, regression, clustering, and anomaly detection, to analyze the overdose data. The classification models were able to effectively distinguish between opioid and non-opioid cases. The regression model provided accurate predictions of overdose severity, highlighting strong influence of the drug-related variables. Clustering helped group similar overdose cases and revealed underlying patterns in the drug usage, and anomaly detection identified rare and unusual cases that deviate from the normal patterns. Together, these techniques provide a comprehensive understanding of the dataset by enabling prediction, classification, pattern discovery, and outlier detection. Overall, the results show that the drug-related factors play a higher role than demographic factors. These insights can support better decision making in public health, such as improving monitoring systems and identifying the high risk cases and developing a targeted intervention strategy. That's all for our assignment. Thank you.